We're working on a new kind of solar fuel that's based on this molecule spinning around here. And what it can do is it can store energy from the sun internally and release that energy later as heat on demand. It works in some ways like a rechargeable battery. It can be charged and reused many times over. In this case, the charging occurs simply by exposure to sunlight. So when the sun strikes this molecule, it undergoes a reaction that transforms it into a higher energy state, or a charged state. And this particular molecule is a special case. It can do this reaction in a reversible manner with no degradation. That means that once transformed by the sun, it stays stable, making it safe and transportable. Then, using a simple catalyst, the molecule can be made to go back into its original state. And as it goes back into its original state, it releases that stored energy as heat. And this makes it essentially a rechargeable heat battery. What we wanted to know is why this particular case is unique, why it's so stable and does not degrade over time, unlike other molecules that have been tried before. So we carried out quantum mechanical calculations in order to understand the heat release mechanism. And what we found was quite surprising. As the molecule proceeds along the reaction pathway from the higher energy state back to the original state, it was thought to have only a single barrier. But the calculations revealed the presence of this intermediate state, which means it has two barriers along the pathway instead of one. And that has important implications for how the fuel is stabilized. And what we find is that the relative barrier heights along this path play a crucial role in its functionality. Using this knowledge, we're now working to develop further improvements in the fuel, such as the use of cheaper materials and also increased storage densities.